So, continuing with looking at using our various functions to model functions, I want to start with talking about what we call optimization problem. An optimization problem is when we have a scenario in which we try to find the optimal solution, the best solution, quite often the largest or the smallest, depending on what the context is. So here I have a question in which we have a visual of two rectangular fields that are to be enclosed with a total of 100 meters of fence. So all of these lines here, including the one in the middle, are total to 100 meters. So we want to find, okay, what values of x and y, what length and width here would allow for the greatest possible area to be enclosed. So first, let's think about the perimeter. If the perimeter is 100, that means I know that x plus x plus x plus y must be 100. Or I know that 3x plus 2y must equal 100. All right. However, we also want to find the total area and maximize it. But the area of this rectangle is quite simple. The area is just x times y. And x and y are variable, but this is what we're trying to maximize. We want to maximize this. All right, so how do we do that? Well, what I need to do is find a function that kind of puts these two equations together. I want to find a function of area, but I want to have just one variable, and then I can graph it and find where its maximum point is. Right now, my function for area has two variables, x and y. And so to take care of that, I look back to my first equation, the one for perimeter here. And I choose a variable, either x or y, and just solve for one of them, isolate one of them. In this case, it doesn't really matter. I'm going to isolate y just because. And so if I isolate y here, I bring the 3x over, so I get 2y equals 100 minus 3x. Divide everything by 2. Y equals 50 minus 3 over 2x, or 1.5x. And so the advantage of doing that, or the point of doing that, is I can now look back at my area function. Instead of writing that as y, I can write it as 50 minus 3 over 2x. And then I have a function, a quadratic function, that has only a single variable. So area is x times 50 minus, I'll write it as 1.5x. And now, what I'm trying to maximize is a single quadratic function, which means I can, for example, just graph it and see where the maximum is. And so that's what I want to do next. I want to graph this. And I can just graph it in the form it's in, and I'll switch to Desmos here. And if I graph it, I see, well, something like this at first, which is a pretty bad graph because I need to adjust my scales here. There we go. So this is showing me the graph of my area function, and I want to find the peak of it. I want to find the vertex of it. And so right there, when x is 16 and 2/3, 6.6 repeating, that'll give me the maximum possible area, and that's what my y value is. My y value is the area, 416.6 repeating. And with that said, let me write that down. So from graphing, I know my maximum is when x equals 16.6 repeating meters. And at this point, although I don't ask for it, at this point the area, it was 416.6 repeating square meters. But now I know when x is 16 and 2/3 in meters, that's the ideal measurement for x. And so therefore for y, all I need to do is take this value and put it back into any of these equations. Probably that one right there is the easiest. And so therefore I can say y will be 50 minus, I'll just go back to 1.5 times 16.6 repeating, or whatever form we use. And if you do that, you should get exactly 25 meters. And so the optimal measurements are x being 16 and 2/3 meters, y being 25 meters exactly. So next question. I have a table of values here relating to the distance that a rocket has traveled when being fired from different angles. And so our first task is we want to graph this data, make a scatter plot, try to determine what would be an appropriate type of function that seems to model the data, and then come up with that model. So first task is, I'll call this my x, I'll call this my y, and make a scatter plot, which I have done already over here. So let me turn this off. Here's my scatter plot, which I'll adjust my scales, because remember my x-axis is an angle in degrees, my y-axis is the horizontal distance. that this is traveled. And so what I have here looks much like a quadratic function. And so I want to make a quadratic model to match this. And I want to use my GDC or technology to create a regression model of this quadratic function, which we've looked at before. And so I've already done that right here. And so my regression model, as I can see when I graph it, is extremely accurate. In fact, if you look at the R value for it, the Pearson's R, it's 0.9997, incredibly accurate model. And so first, let me write down that model there. So the equation of that, what I just showed you. So my quadratic model and again, I'll round everything to 3 significant figures, was approximately negative 0.261x squared plus 22.5x plus 24.2. And again, that was determined using my regression feature, which I use in Desmos, and you can use in any of the graphing calculators. And so once I have that, now I'd like us to use this to determine the optimal angle to maximize the horizontal distance. So it's an optimization question. So going back to my graph, and again, now it's the graph in blue that I care about. So I'm going to turn off my scatter plot. So this is my model, which again has a very, very, very strong correlation to the data. The optimal angle to maximize our distance will be the vertex of this, which is right there. And so I can see from looking at these values, that means when my angle is about 43.2 degrees, the maximum distance will be about 512 meters. So I'll just write this down and then we're done. All right. And keep in mind, if the scatter plot seemed to model a different type of function, I would use a different regression model, but clearly the quadratic model was a good one. All right, lastly, I want to talk about direct and inverse variation or proportionality. So I'm going to go back to the top of the notes here, but in general, if we say that two variables have a direct variation, then the equation can be represented as just y equals some constant times x, which means when x is 0, y is 0, or whatever they are. And anytime, which is a linear function with a y-intercept of 0, a very simple linear function. And also all linear functions like this that start at 0, then we can say are an example of direct variation. And that's quite simple because you deal with linear functions a lot. A little bit trickier is what I want to focus on is inverse proportionality or inverse variation, which is similar, but it's where of my two variables, it's not the constant being multiplied by x, it's the constant being divided by x. And in fact, all three of these are equivalent. Just for example, if you want to look at any of these forms, for example, to go from here to here, just multiply both sides by x, and then you get this, and here divide both sides by y, and you get this. They're all equivalent. So anytime we hear any sort of phrase about inverse variation or inverse proportionality, then we know that we can model our function using any one of these, where k, again, is the constant of proportionality. When we had direct variation, k is the same as the gradient or the slope. And so in this case, we look at this question about a seesaw. Right off the bat, I can see it talks about how the weight varies inversely with the distance of the object. And so the two things we're comparing, we have weight, I'll put mass for weight, because the units we actually have here are in kilograms, which is a unit of mass. And I have distances, actually I have two different measurements of mass here. And my distance, 150 centimeters, I'll use D. So how these two are related, I know I can relate with any of those equations. And I'm going to start with the first one. This y equals k over x, or any variation of that. In this case, instead of y and x, I want to have weight and distance be my variables. It doesn't matter which one's which. I'm going to change y to mass. I'm going to change x to distance. The key is that proportion constant of proportionality is the fancy word for it. That is the k in this case that we need to figure out. Okay, so with that said, what we're told is this. We're told that if a person has a mass of 70 kilograms and they're sitting 150 centimeters from the fulcrum, that's the first half. We want to know the other half is how far should someone else be sitting if they weigh only 50 kilograms. And so first, let's focus on what I've underlined. And so I know that if someone has a mass of 70 kilograms, so 70 equals k divided by, and they set it at a distance of 150, I can now figure out what that constant of k must be. It's going to be 70 times 150. And so that constant k must be 10,500. And so if this was direct variation, that would be equivalent to my slope. This is inverse variation. And so now I can look at the second half. So if I look at the other part now, so if someone has 50 kilograms, that means their mass is 50. I know this must be, instead of k, I can say 10,500 divided by the distance, which is what I'm trying to figure out. Or, what may be more handy is to use a rearranged version of this equation where I have the distance here and I have 10,500 divided by 50 here. Then we just get directly to what we're trying to figure out. Because again, keep in mind, all I did there is you can either imagine I just solved for the variable d, or going back to my key points here, is all three of these are equivalent. Essentially, I went from kind of this form to this form. And everything here is equivalent. And so now it's pretty much done because the distance we should sit is 10,500, that constant divided by 50, which is 210. So what this tells me is that if you have someone who is 50 kilograms and someone who is 70 kilograms sitting on a seesaw, or then the person who's 50 kilograms should sit 210 centimeters from the fulcrum, from the, this part right here, whereas a person who's 70 kilograms should sit 150 centimeters. If they do that, they are going to be balanced. And again, the key part is what I've highlighted in yellow here. As soon as we saw that we are describing a function in which something varies inversely, then I knew right away I have some sort of setup like this. And one of my first things to figure out is that k, that constant of proportionality, we call it.